All right, so we're going to be starting chapter 4 today. Chapter 4, we get into looking at two variables instead of just one variable and talking about the relationship between those two variables. Oftentimes, when we're trying to create a visual representation of those two variables, we use what's called a scatter plot or a scatter diagram. And that allows us to look and see how the two variables are related to each other. We generally put our explanatory variable as our x and as our response variable as the y. And then we can see as we change our explanatory variable, what happens to the response variable. So let's get into some vocab. And again, this first section is stuff that we've already done. We covered it earlier in chapter 1 when we talked about what a explanatory or what an explanatory variable and what a response variable are. So you should have knowledge of those two vocab words, but if not, they're defined again. And we did these two examples as well. So smoking leads to lung cancer. Our explanatory variable in this case was smoking, and our response variable was the lung cancer. And then below, completing homework leads to good grades. Our homework was the explanatory, and our grades were the response variable. So theoretically, the more homework you did, the better your grades would be. All right. Now we're going to talk about how do we create a scatter plot or a scatter diagram, and what do all the different components mean? So in order to create a scatter plot, you have to be recording two sets of numerical data, and you have to have a hypothesis that those two sets are related. So you could do something like age and height. You could do height and weight. You could do age and how fast you've driven, things like that. But you're comparing two of them, and you're going to have to choose one of your variables to be the explanatory variable. And then the other one would be the response variable. Now, sometimes it can be confusing, and you can switch around which one of those is explanatory and which one of those is response, especially if you're doing an observational study. It can be hard to know which of those things caused the other one or was the kind of the triggering effect, the explanatory variable. And we'll actually get into some of that a little bit later. So when you're drawing it, you set it up as a grid. Typically, you only need like 1/4 of the grid. You're typically only going to have positive x values and positive y values. And if that's the case, you only need quadrant 1 of your Cartesian coordinate system. You don't need the full graph, just quadrant 1 where both x and y values are positive. You have to determine your explanatory and response. Explanatory is x, response is y. You need to make sure you've labeled and titled everything, and then you plot your points. So here we have a set of data. We're going to talk about height as our explanatory variable, or the x value, and handspan as our response variable, or our y. Now, they don't give units for this. I've looked into it a little bit. These heights are going to be in inches. So 71 inches tall, that's almost 6 feet. And handspan is in centimeters. Handspan is the distance between thumb, the tip of your thumb, and the tip of your pinky, as far out as you can stretch them. And that's going to be your hand span. And when you're looking at this, we are going to treat it like height is explaining your hand span. So we think the taller you are, the bigger your hand should be, or vice versa. The shorter you are, the smaller your hands are going to be. That's how we're looking at it. That height is the thing explaining hand size. So pause this video, take a second, go through, come up with what you think is a good scale, and then plot all of these points, making sure you label your X, your Y, and give this graph a title. And then come back and we'll check to see how we've done. All right, so when I started this, I started with 64 here. I do a little graph break, 64, and then we'll go up by 1. So 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75. And then for my hand span, I went in increments of full centimeters. So I started at 18. Sorry, I started at 18. Again, graph break, 18, 19, 20, 21, 22, 23, 24. And then you could go up higher. It wasn't big enough to make it so I could have every half centimeter. So this was the scale I chose. And then you can fill in as many of these as you want to make it easier for you to find those. And then we plot points. So our first point that we have is the ordered pair, 71 for the height and 23.5 for our hand span. So 71 and 23.5, and we plot a point. And then we continue doing that for all of them. All right, so we've plotted all of our points. We've made sure to label both the X, Y axis and give our graph a title. So labeling is going to be fairly straightforward. You're just naming which variables you have for our explanatory and our response. So our explanatory variable is height. Our response variable is hand span. And then a common way of titling a scatter plot graph is by naming those two things and putting verse in between. So this is height versus hand span. So essentially you're comparing those two, or height and hand span, or height and its effect on hand span, something like that. You're letting your readers know that you're comparing those two variables. So we have what our graph should look like. Now, we are going to be using this information later. So go ahead, put this in your calculator. So in my calculator, when you go to look at it, or when I show this to you, these are going to go into list 1. These are going to go into list 2. So pause the video, put these into your 2 lists. And when you're done, it should look like that. So you've made sure that you've put your heights in list 1, your hand span in list 2. Again, which lists you put them in doesn't matter as long as they're 2 separate lists and you remember which list goes where. And the next thing we're going to do is I'm going to show you how you can use your calculator to graph or to plot a scatter plot. So get back to our home screen. And next, instead of going to y equals, which is what you've been using when you want to graph something, we're going to hit second and we're going to go into stat plot. So second y equals brings us to stat plot. This is where we will be doing, or where you can do a lot of different statistical graphs. And we're just going to click on plot 1. We're going to make sure it's turned on. Mine was already on. You can see there's different types of graphs here. There's a histogram graph. There's a box and whisker with outliers, box and whisker with no outliers, all sorts of different things. The one we want is a scatter plot. It's that very first one. And you notice when I went from a box plot to a scatter plot, it changed how many variables I had. So here, watch these right here. I have an X list and a Y list right now for my scatter plot. But when I go to a box and whisker, it gets rid of that Y because there's no Y list for a box and whisker. So we're going to go back and we get here. It changes it to an X list and a Y list. My X list is in list 1, Y list is in list 2. If you needed to change those, you could scroll down and change them to whichever list you needed to. And then you can change the color. Yours may not have a color, so that may not be an option for you. Next, once you've set this up, we're going to go to Zoom. And number 9, it is Zoom Stat. What this does is it goes into the lists that you've used, and based off the lists you've used, it creates a window that will allow you to see the points you've picked. So if you just do your regular, so I'm going to go to Zoom Standard. Forgot I had a graph there. So if I go, I don't have a graph. All I have is those 2 lists, and I set this up. You don't see anything because the window isn't correct. But if I go to Zoom and hit number 9, Zoom Stat, that is my scatter plot. And then you can go through and you can double check to make sure. If you hit trace, it'll give you all of the different points. And so you can go through and you can double check to make sure that your graph looks like the graph that your calculator produces. And that gives you a quick way of double checking to make sure you did it correctly. All right. There are different types of relationships when we're dealing with scatter plots. We care about linear graphs. In this class, the only type of regression we're going to be looking at is linear regression. And so we, in this class, break it up into linear and nonlinear relationships because we only care about linear. Everything else, anything that's nonlinear, we're not going to deal with in this class. If you take different types of statistical classes in college, you will get into different types of regression. If you take any type of like biology where they're dealing with population, or chemistry, if you're dealing with half-lives and things like that, you will use exponential or logarithmic regression. If you get into anything in like the sound industry or light industry, you'll have sinusoidal regression. So you're converting everything into a wave. And so there's different types of regression based on what applications you're using. For this class, we strictly focus on linear regression. And so these first 2, both of these are linear relationships. As X increases, Y either increases or decreases. So on this first one here, we have a negative linear relationship. As X increases, Y decreases, but it's consistent. It appears that we are drawing a line. Now, the closer those 2 kind of boundary guides are to each other, the closer our correlation coefficient will be. And we'll talk a little bit more about the correlation coefficient in a second. So the tighter you can make kind of those boundaries, the closer or the more closely Y will follow X. And then we have a couple other examples. These are nonlinear. Now, there's clearly a relationship in that one I just looked at. It is a quadratic regression. So it forms a parabola. Over here, again, this is nonlinear. Now, this one's a little bit trickier. It looks like it could almost be linear, but it is going to follow an exponential model. So that is not a linear regression either. And same thing here. Another exponential curve. And then this last one. This last one is tricky because it looks like my boundaries are straight lines and they're fairly close together. However, in order for us to have a relationship of any kind between my variables, as I change X, it has to affect Y. Y has to go up or go down, but there has to be some relationship about when I change X, I can predict what's going to happen to Y. Well, in this case, it doesn't matter what I do with my X. y is staying roughly constant. So in this last case, it's not only nonlinear, we say there is no association. Y does not depend on x. I can plug in any value for x, y is going to stay roughly the same. So if you have a horizontal line, that means there's no association between x and y. It does not matter what x value you plug in, your y value is unaffected by that. So we talked briefly about the two different types of linear relationships, and those are positive and negative. So when we have a positive association, you can think of that as a positive slope, meaning as I increase my x value, my y value will increase as well. Now, that doesn't mean you won't have some points that don't fit directly in. So if we go back to look at our height versus handspan, this would have a positive correlation, meaning as x increases, y tends to increase as well. However, we have a few points over here that don't fit that. As we increase x from here, it actually drops down. And that's okay. Not every point has to work on this. That's why it's called a regression line. If it worked perfectly, then it wouldn't be a regression model. It would simply be a function. So we are talking about kind of the band between those kind of guidelines. As long as those two guidelines are positive, then we consider this to be a positive association or positive relationship. An example would be as speed increases, stopping time increases. So the faster you're going, the longer it's going to take for you to stop. And so as your speed increases, the time also increases. Next, we have a negative association. And again, what that is implying is that if we were to draw kind of our boundary guidelines, those would have a negative slope to them. An example of that is as your age increases, your vision decreases. So how far away you can see something gets shorter and shorter, meaning you have to get closer to things in order to see them as you get older. So that has a negative relationship. And then about that last graph, you can have things that have no association. So they're not related to each other in any way. And when that happens, that's when you see that kind of horizontal band of points. An example of that would be how long it takes you to get to school and how fast you can type. Those two things have nothing to do with each other. It could take you 1 minute or 1 hour to get to school. It does not affect your typing speed. There's no correlation between how close you live to school or how long it takes you to get there and how fast you can type. Next, when we're talking about those linear relationships and we're talking about how x affects y, the stronger the relationship between x and y, the higher our linear correlation coefficient is going to be. So this is a number that basically tells us how closely y follows x. So it measures that strength of linear association between x and y, and it measures the direction. So your R, your linear correlation coefficient, which is R. R is the variable we use for that. It can be positive or negative. Positive means that there's a positive association. Negative means there is a negative association. The strength or that number of your correlation coefficient can go between -1 and +1. You can almost think of it as what percentage or how much of x goes into y. So if you have a linear correlation coefficient of 1, that means you have a function. So that means this line has an R value of 1, which means if you draw a line, it will hit all of the points exactly in the middle. So the closer to 1 you get, the narrower those guidelines are. The closer together all of your points are to forming a straight line. So when we were looking here and we talked about kind of our guidelines and how spread out those guidelines are, the closer we can make those guidelines here, these lines that I drew in, the closer we can put those together and still contain all of our data points, the stronger our R value is going to be. The closer we get to 0 for our R value, the more spread out or the more cloudy all of those points look. And when you have a R value of 0, that means there's no association. There isn't a way of using X to predict Y. And then the same goes for a negative R value. If you have an R value of -1, again, that means all of your points fall in a straight line. However, this time the line has a negative slope. Now, another thing that can be tricky is you could have a perfectly straight line. So you can have an R value of +1 or -1. It doesn't tell you the slope of that relationship. So you could have a graph that sits perfectly and everything looks like that. That would have an R value of 1. You could also have another set of data and the slope is like that. This will also have an R value of 1. Your R value doesn't tell you the slope. It simply tells you how related X and Y are to each other. And so the closer we are to +1 or -1, the stronger the association between our two variables. An R value of 0 means there's a very weak or no relationship between our two variables. And again, it's not no relationship, it's no linear relationship. If you look at a quadratic regression, so if we go back up to our different types of graphs, and we look at this one right here, that would also have an R value that is close to 1, even though there's clearly a relationship between X and Y. Because it's not linear, our R value is going to be close to 0. R is only used in this class for our linear relationship. So it does not work on non-linear relationships. So let's go through and kind of get an idea of what different types of relationships would be. So we have these first two, and you can see that these are positive because both of those guidelines are pointing up, and that's a very narrow band. So that would be a strong positive association. Here, both of those are negative. It is also strong. It's actually stronger than our positive one because those two guide bands or guidelines are closer together. Now this one here, we try and keep that there, try and keep this one like that. So those are both positive. So they're both pointing up. However, that's a very cloudy set of points. Those bands are very far apart. That is a weak positive relationship. They are both going up, but it's a very wide band of points. When you plot those points, it's very cloudy. The closer those points are together, the closer they are to forming a line, the stronger our R value is going to be. Here, because our guidelines form a band that is horizontal, we have no association. Again, if our points form a horizontal band, there's not going to be an association because we have to have a predictable change in y when we change x. This next one, again, there does not seem to be a discernible increase or decrease as we're moving from left to right. So again, this one has no association. This one we can see is negative. However, it is weak because that band of points is wide. So the narrower that band, so if we go to the top, the two that were strong, the closer all of those points are to falling in a straight line, the closer to +1 or -1 we're going to be. The further away those points are, the closer to 0 we're going to be. And this is our formula to find our R value. Now it's made up of essentially 3 different components. So we have that x minus x bar divided by s sub x. So that should look somewhat familiar to you. We just talked about it in 3.5. That is the formula to find a z-score. So essentially, z sub x would be x minus x bar divided by s sub x. Now, s sub x means the standard deviation of the x values. So we have z sub x, and then our y would be y minus y bar over standard deviation of the y's. So we find the z-score of the x's, we find the z-score of the y's, and then we multiply those two values together. So those are the first 2 components, z-score. And again, remember, z-score is talking about where are you compared to the average value. So we look at each individual data point and say, hey, are you above or below average? And that's what gives us z sub x. And then we do the same thing for the y. So again, each data point consists of an x and y. So for each data point, we're finding the z-score for the x and the z-score for the y and multiplying those 2 things together. And then the last part 3, this multiplication here is finding the average. So we find the x and the y z-score for each point, multiply those together, add them all up, and then we find the average. And when we do that, that's what gives us our R. So let's go back to our point that we found, or scatter plot that we graphed for hand and or height and hand span. So essentially what we have, going back here, we have this plot. I want to find x bar and y bar. I want to find my average x value and my average y value. So I'm going to quit. I'm going to go to stat, calc, and this time instead of doing 1 variable statistics, I want to do 2 variable statistics because I have both an x and a y. So I plug in my x list, I plug in my y list, calculate that, and there it gives me an average x at average y, a standard deviation for my x. And if I scroll down, there it is, standard deviation for my y. So it gives me all the information I need to find those z-scores. So my x bar is 68.125. My y bar is 21.1875. So here, x bar 68.125, y bar was 21.175. 21.1875. So if I draw those on my graph, so my average, that's roughly x bar, and then y bar is somewhere around there. Now you can see which quadrants most of our points fall into. And by looking at that, it also gives us a good idea of whether or not we're going to have a positive or negative association. So when we look at these lines, anything that falls below the y bar line is going to have a negative YZ score. Anything that falls above the average Y value will have a positive YZ score. So if I'm creating a sine graph for these quadrants, anything down here is going to have a negative Y value for the standard deviation or for the Z score. So I'm essentially creating signs for X or Z sub X and Z sub Y. So below the Y average, they're both negative. Above the average Y, they're both positive. Now, for my X's, if it is to the left of X bar, we're going to have a negative Z score for my X. If I'm to the right of my average X, I'm going to have a positive Z score. Now, based on those averages, so my X bar and my Y bar, notice the two kind of quadrants that the majority of my points fit into or fall in. They fall into the negative negative quadrant and they fall into the positive positive quadrant. And remember, in order to find my R value, I am multiplying those two Z scores together. So when I multiply a negative and a negative, so the points down here, I end up with a positive number. And when I multiply a positive and a positive, I end up with a positive number, which is why after I've multiplied those together, added them up, if most of my points fall down here and up here, I end up with a positive association. If I had some other graph and those imaginary points were up in this quadrant here where it was negative positive and down here where it was positive negative, that would give me a negative R value because when I multiplied my two Z scores together, one of those Z scores is positive, one is negative, which would make the result negative. So that's why, or that's how our R value turns out positive or negative based on what my graph is looking at. It's based on those Z scores and how they relate to each other, how the X Z score and the Y Z score relate. Are they both below or are they both above, or is one above and one below? All right, now back to our calculation on how we actually calculate Z score. And one of the benefits is going to be that we don't actually have to calculate our Z score by hand. So these directions here show you how you can calculate the linear correlation coefficient using your calculator. And I'll demonstrate that same thing now. I'll be following these same rules. So first thing, we have to make sure that we have put our two sets of data into our calculator. So list one, list two. Next, now not everyone is going to have to do this, but I'm going to show you. And if you're not sure, do it anyway. It doesn't hurt. You should only have to do this once. We're going to go to second, catalog. Catalog shows every function that your calculator has. And with this, we're going to scroll all the way down until you see diag on and diag off. It's alphabetical, so scroll down until you start seeing the D, and then you can start slowing down once you're into the D's. And here you go, diagnostic off, diagnostic on. We want to click on the diagnostic on. So you click on that, click it again, and it'll say done. Once you've done that, you won't have to do it again unless something happens and you completely reset your calculator. Next, we go to stat, calc, and instead of one variable statistics or two variable that we've been dealing with, we're going to go to number 4. And from number 4 down quite a ways are all the different types of regression lines or regression models that your calculator can come up with. Number 4 and number 8 are the exact same. I have no idea why there's two of them, but they're both linear regression. But we have quadratic regression, cubic regression, quartic, which would be something to the 4th power. Number 9 is natural log regression. Then we have exponential regression. We have a power regression model. We have a logistic, so using logs. And we have a sinusoidal regression. So we have all sorts of different types of regression models that your calculator can use, and you will use those depending on what classes you take in college. But for our point, we're going to go back to number 4. We're going to hit enter, make sure that we have our X and our Y list correct. And then once we hit enter, it'll give us 4 pieces of information. A and B we'll use in 4.2 when we talk about our least squares regression line, which we just found using that. For this section, what we care about right now is R. R is equal to 7.53. That's the R value for our height versus hand span data. So that's a fairly strong relationship between those two variables. Now, when people talk about strong or weak, it's tricky because it all depends on what you're talking about. If you're talking about models that are doing something with physics or math where you have kind of a hard science, where the data should fall very closely to each other, you'll get very high R values. So if you're in physics and you're trying to see if your calculation is correct, and so let's say you're mapping positions of planets and times of day, those should be fairly exact. We should be able to predict incredibly accurately where a planet's going to be based on the time of day. And so those R values are going to be incredibly high because it's not just a correlation. There's actually an underlying thing, gravity, that is affecting where that planet's going to be. So in kind of more math heavy sciences, you're going to get very high R values. R values that are very close to either +1 or -1. However, if you're in psychology or sociology, where you're dealing with human nature, those are going to be much lower R values in order to consider something statistically relevant. So you may have an R value of like 0.3 if you're dealing with something in sociology, and that may be considered a high R value and worth looking into. It just depends on what type of science you're looking at, whether an R value of 3 is good or bad, or an R value of 9 is good or unachievable because you're dealing with human nature. So it's tricky to generalize an R value as to whether it's strong or weak. So here we have 2 examples. I would like you to go through, put those into your calculator, and then find the R value, the correlation coefficient. So find both of those, and then we'll talk about the answers in a second. So first one, after you put everything in, you should get an R value of 0.99. That's a positive association, and no matter what you're dealing with, an R value of 0.99 is a strong relationship. So that data is very close to being in a straight line. Next one, you put all of that data into your calculator. This gives us an R value of -0.672, and that tells us there's a negative relationship between X and Y. 0.67 is in that kind of gray area where, depending on what you're talking about, that may be considered relevant or not relevant. So we'll just say it's negative. We don't necessarily need that positive, that strong or weak attachment. It's just a negative relationship. And this is kind of the tricky part of stats, the part that the human brain naturally has a hard time with, which is no matter how strong the correlation is, it does not ever make causation. So even if you have an R value of 0.99999, that correlation does not mean causation. And it is a common tactic to think, well, if I have a really strong correlation, then that makes it a causation. And it doesn't, because when we're talking about correlations, it doesn't do a cause and effect. We chose X to be our explanatory, but if we reversed it and flipped our two variables, that wouldn't necessarily change our R value. And so it doesn't give us a causal link. It just says these two things are related to each other. And so you have to be very careful about that. We give an example of why causation might not be, or correlation may not be causation. I have a better one, and I'm going to show you a website of ones I think are actually fun. And if you, as a book recommendation, if you're ever interested in this, or you find these types of things interesting or statistics interesting, there's a series of books called Freakonomics, and there's Super Freakonomics. And I think there's a third one called When's the Best Time to Rob a Bank? But it looks at kind of common everyday problems through the eyes of an economics major, which deals a lot with statistics. So it talks a lot about the difference between causation and correlation, and things like that. So those are some really fun, interesting books that have a lot to do with math, but are written in such a way that it's a very easy, fun read. And this is where I got this example. In the summer, so as temperature goes up, sorry, not that. It is as ice cream sales go up, crime rate goes up. There's a high R value, there's a high correlation between ice cream sales and crime. And so just because there's a high R value, does that mean that ice cream sales is what causes the crime? And the answer is no. Just because people are buying ice cream, it's not like they're going to buy ice cream and then robbing the ice cream store or eating their ice cream as they go to rob a bank. I kind of gave away the answer, but the answer is there's a lurking variable, and that lurking variable is temperature. So temperature, as temperature goes up, that increases ice cream sales. And so that is why the ice cream sales go up. Now, the other part doesn't necessarily have to do with temperature, but it has to do with the time of year and what happens during that time of year. So what time of year do we get higher temperatures? We get higher temperatures during the summer. So what happens at the summer that may increase crime? Summer vacation. So the lurking variable is the time of year. Crime goes up when students aren't in school because that gives students 8 hours, 9 hours, 10 hours more of unsupervised time when they'd normally be in school. So during the summer, crime goes up because there's a whole group of people who used to have adult supervision during the day that may no longer have that adult supervision. And ice cream sales go up during the summer because the weather's warmer. So there's a lurking variable that connects both ice cream sales and crime, but they're not related to each other. So it's not a cause and effect between ice cream sales and crime rate. That causal link comes from the temperature and ice cream and the time of year and crime, but that's a lurking variable that you might not think about. And so that's why correlation never equals causation. And then the website is called, if you just look up spurious correlations, it brings you to this website. And it is a whole list of scatter plots that have high correlations, but clearly have no causal link. So this first one is the total revenue generated by arcades and computer science doctorates awarded in the US, and that has an R value of 0.985. So that's a very strong link, but there's nothing that suggests one of those things causes the other one. Also, when you're looking at this website, if you go to look at this website, I think it's fascinating about what information is out there. In order to make this scatter plot, you have to be able to find the total revenue generated by arcades by year, which means that's recorded somewhere where you could go out and do some research and find that information. Next, worldwide non-commercial space launches and sociology doctorates awarded. Down here, we have civil engineering doctorates awarded and per capita consumption of mozzarella cheese. So again, besides showing that you can have extremely high correlations between two totally non-related variables, I think it's fascinating to see what information is being kept track of. It is possible for you to go out and figure out how much each state consumes or each country consumes in cheddar cheese. So I think that's another fascinating piece of information. All right, so we talked about correlation and causation. And the next thing is, in order for us to think that there's a linear relationship between two things, we have to check our R value against a predetermined critical value. And so in order to do that, we have to have a table. And that table you can find in here on these notes. It says critical value linear correlation. If you're doing your homework, this table is going to be on any question that you need it. And when you take your test, I will attach this table to your test. But essentially, this table has two pieces of information. The first piece on the left-hand column, it has the number of data points. It has your sample size, N. And on the right, it has a critical value. So what this says is, let's say if you have 20 data points in your data set, in order for us to say that there's a linear relationship between X and Y, our R value has to be greater than 0.444. If our R value of our data sets comes out to be less than that value, that means we don't have a linear relationship between our two things. So that's how we use this table. Let's go back to our notes and then actually test out. So, sorry about that. Here we find our R value and then we take the absolute value. So we're always looking at the absolute value of our R and comparing that to our critical value. So let's look at a couple of examples and then we will be done with this section. So is there a linear correlation coefficient if our R value is 0.896 and our sample size is 6? So R value of 0.897. So step one, find the absolute value, 0.897. And next we need to find our critical value. So we go to our table. We look at 6. It has a critical value of 0.811. So 0.811. And then we check to see, is our R value, so is the absolute value of our R greater than our critical value? Yes. So a linear relationship exists. So because the absolute value of our R is greater than the critical value, we have enough information to say that there is a linear relationship between our X and our Y variable. All right, last one. Step one, absolute value of R is 0.067. Our critical value, this time our sample size is 9. So we come down to 9 and we get a critical value of 0.666. So is the absolute value of R greater than our critical value? So is 0.067 greater than 0.666? It's not. No. And so no linear relationship exists between X and Y. All right, that is the end of 4.1. In 4.2, we will be talking about creating our least squares regression model, which creates that line of best fit between linear relationships.